Hi, this is Richard Southern from the National Centre for Computer Animation, and this is a talk that I've given to basically the general public relating to how one might model adaptive human locomotion. And it brings together principles from a variety of different subject areas, including motor control, robotics, and biomechanics, to basically come up with a theory for how we might describe motion adaptation, and particularly locomotion adaptation for adaptation from mathematical principles. So just decoding the title of the talk, obviously modeling, when we're referring to modeling, we're basically saying we're trying to take some or other complex phenomena, which is, in the case of locomotion, is extremely complex. But of course we could be referring to any complex phenomena such as the stock market or geological processes. Modeling is the process of reducing those down to something which I consider to be understandable, which might mean in some form which is easier to make judgments or decisions. In our particular case, we're modeling locomotion for a variety of different applications, potential applications, which I'll talk about in a little bit. When we're talking about adaptation, we're talking about modifying your behavior, either implicitly or explicitly, to compensate for some sort of change. And when we talk about the change, we're talking about change in either yourself, so let's say you stubbed your toe and you're finding it difficult to walk, or the environment. So the environment might you might be walking on a slippery surface as opposed to a regular surface, or perhaps you're walking up or down a slope. So how would you try to maintain the same type of motion but adapt it to a different type of environmental condition? And when we talk about locomotion, of course, we're talking about any type of method of moving from one point to another, but in this particular work we focus in on walking, but the same principles should apply to models for running and hopping, or in fact any periodic system. So locomotion is particularly difficult to understand. The main reason is that it's based on a number of different biological processes, which range from the chemical to the electrical, and of course at the same time you have the mechanical system, which is of course extremely complicated and different in every person, which is your joints, bones, and the distribution of mass. Now, the other issue of trying to model this phenomenon is that you don't really know much about your environment potentially. So all of these factors combined basically tell us that there's no existing model that is as stable, adaptable, or as energy efficient as a human. So we'll look at some examples of robots that have been built, which are very expensive to build and run, but they are still quite far away from the energy stinginess of a human walker. So why do we need to model this? It's not necessarily obvious, but certainly the robotic devices, such as the one in this picture, have been widely used already in aiding gait rehabilitation. So helping people perhaps who have suffered from stroke or other kind of injury, spinal injury potentially, to recover their walking ability through practice. Now, the purpose of these devices is to provide resistance where needed and to provide assistance where needed, in order to steer the gait into the correct pattern. Now, what you need for that is you need a full understanding of how the human motion is happening, and in particular in the particular participant's case. So understanding how human motion would be modeled enables us to tune these robotic actuators to assist in the rehabilitation and increase recovery time. Another quite obvious application of locomotion modeling is in the development of bipedal robots. So this is a quite obviously a Boston Dynamics robot. You'll note from its the way its legs are moving up and down that the gait is not necessarily as natural as a human walker, and I'll discuss that a bit later. But also the other thing is that while it's incredibly adaptable, walking in a very dangerous or difficult terrain, and it's capable of a number of interesting complex adaptation strategies. A lot of this is due to the large number of sensors and other devices that are on the machine, which obviously weigh it down and use up a lot of energy, such as the method to look ahead and survey the terrain in front of it. So ideally we'd want to design robots or robotic controllers that don't need all of the sensor capabilities and are still able to maintain as stable a gait as possible, and thus it would reduce the weight and reduce the energy consumption. And just as an example of how fragile these things are, this is the 2015 or compilation of robot accidents during the 2015 DARPA challenge, when these robots would have to try and complete a number of basic tasks such as opening doors or walking on uneven terrain, and just sort of demonstrates the complexity of doing things which humans might find absolutely trivial. So here's another example where locomotion modeling is useful. This is a project between Bill Sellers at the Animal Simulation Laboratory at University of Manchester, and there were a number of other collaborators on this work. So this image is from a study of the Natoli footprints, where they built the biomechanical structure of a potential of a walker from this period, based on the skeleton of the hominid Lucy, and they were able to demonstrate that these early hominids were likely to have walked upright rather than using the bent knee gait. So this is an example where researchers helped us inform the biology or biological development of humans. And here's another example of where locomotion modeling is applied. So locomotion models are widely used in animation and visual effects, particularly when simulating animals or people in expensive shots which consist of crowds. So this short sequence required a large number of running and falling horses to be simulated, and a team at Moving Picture Company, which was also responsible for the technology behind World War Z, developed a model for simulating this complex behavior in a way that seamlessly blended with the actual footage. And unlike in older productions like Ben-Hur, no horses were actually harmed in the production of this film. So the goal of this talk is to present some contemporary advances in motor control, robotics and biomechanics, and that's really based around the principle of equilibrium point hypothesis. And then we're going to try and distill these into the motor control as the equilibrium point hypothesis, and then we're also going to talk about some dynamical systems and some robotic systems as well. And we're going to put these together into a coherent model or theory for controlling motion adaptation. So I'm going to try and define, without any symbols, a mathematical model or machinery to help us realize this theory, and we're going to apply it to a simple model for walking as a proof of concept. So start by posing the question, why do we get better when we practice? So this is obviously Venus Williams winning the Australian Open while being 12 weeks pregnant, which is probably a physical feat that most of us cannot aspire to achieve. But quite often the answer to this is often passed off to the extremely complex mechanism, which is the brain. So you're seeing a collection of neurons and synapses all connected together into some sort of unbelievably complex structure. But in truth, the brain probably can't control our motion. So if we consider the complexity of motion, in our arm alone there are 23 muscles or muscle groups. So each one of these muscles, well, they have different functions. Some will extend and some will contract, They all apply different forces depending on the magnitude of the signal that gets sent to them. And all the muscles take time to heat up on activation. So what you end up with is a infinitely complex optimal control problem, which would be daunting for even the world's most powerful supercomputers to resolve. And given the limited computing resources of the brain, so the speed of the synapse, so I'm not 100% convinced by this 100 milliseconds to compute, but the speed of a synapse is about 150 meters per second. So if you consider the travel time of a message to be sent from the brain down to a muscle and then back up to the brain again in order to process, the ability to actually compute the response to a particular stimulus would be impossible based on the limitations of the synapses and the neurons in the human body. So this is clearly not what's happening. So the brain is certainly not the mechanism that is helping you balance on a wobble board or allow you to hit a ball effectively in tennis. So the way to put that is that optimal control, which means that the brain is calculating the optimal path or trajectory of motion, is highly unlikely. So a theory of motion control is instead to say that the central nervous system is responsible for issuing the instruction, but the processing of the action is distributed about the rest of the nervous system. So in the figure, there's the brain and the spine here in yellow would represent the central nervous system, and the blue cables or blue connectors are the rest of your nervous system, which are all ultimately connected with your muscles. So the idea is that there's effectively a cascading hierarchy of activations which trigger via the central nervous system, and I'll talk about what it triggers in a second. So this is conscious or subconscious through sensory stimulus. So this allows you to react very quickly from some sort of visual stimulus, for example, to dodge a brick being thrown at your head or something. And the brain, of course, specifies the goal of the task. So what it might do is it might say do this action quickly. So and it might also say where it wants you to end up after the action. So the body determines, using some form of existing solutions, which we'll come to, of how this task is going to be completed. So the central premise here is that the central nervous system issues essentially a broad instruction, and the rest of the nervous system essentially calculates applies some principles to achieve that function. So this actually can be drawn in this diagram, which I've appropriated from a book by Jian and Latache, Motor Control Theories, Experiments and Applications. So the central nervous system, which is the brain and the spinal column on the left, basically, as I said, would trigger an efferent pathway is the pathway that goes from the central nervous system down to the muscles and activates the muscle system. And as you can see, Latache and Jian have split this process into three different states, if you like, one which defines the configuration of the body. So the efferent pathway follows. So where was I? Okay, so the states of the body, the states divide the different layers, if you like, of the neuron and synapse pathways. So one would define the state of the body, and then if you drill down further, it's the state of the individual joints, and then of course you have the muscle state, which defines the individual muscle activations. And what's important about this diagram is that you see both there's a downward pathway, which is the efferent or activation pathway, and then there's the afferent or sensory pathway, which feeds back up the chain all the way back to the central nervous system. Now, what this does is essentially allow for a reconfiguration of the neurons and synapses in the nervous system, to allow it to improve for example, how effectively it performs the action. So what that does is it creates a self-organizing network, which is basically improving the configuration to make it a more effective arrangement of neurons. And that is where we get better when we practice tennis, because what's happening is by repetitive action and by getting the sensory feedback from our actions, our actions are becoming more effective. So we don't start with nothing. When we're born, it is postulated that we start with a set of motor synergies. So a very simple one would be that when we bend our elbow, we have muscles on both sides of the arm pulling and pushing simultaneously in order to achieve the bending action. So some of these obviously we're born with, and some of these we develop over time, but these motor synergies, if you like, are reusable elements of motion. So what probably will happen is that our neurons and synapses will become configured so that these muscles will very rarely be triggered independently. So in the same way as we will notice that a baby will be able to reach and grasp and kick from birth, these are considered to be the muscle synergies that we're all considered to have. And others are learned through repetitive actions. But another thing about motor synergies is that we don't generally move the way that we want, we move the way we can. So while a whale was born with certain motor synergies, probably due to its evolutionary inheritance, because it was placed within water rather than on land, it has evolved motor synergies that make it more effective at moving through fluid. And the principle here is that it is really expensive to fight against your biology and the environment in which you're immersed. So moving further from motion synergies or motor synergies, we can start talking about motion primitives. So motion primitives are defined by essentially the efferent neuron stimulation in the central nervous system. So basically, if we trigger an action, and this is really by triggering a single neuron in the central nervous system, we will create an action will result. So the classic example of this is the waving frog, and it was possible. So there's a research group led by Busy, and this was published in the Linear Combinations of Primitives in Vertebrate Motor Control in '94. And in this work, they were able to trigger the individual motion primitives by electrical stimulus to the spinal column of the frog. And this tells us that that has triggered an entire sequence of muscle activations, potentially multiple motor synergies, which essentially were triggered all by the single electrical stimulus to the central nervous system. So what that tells, and also another thing which is very interesting, is that the frequency and amplitude of the electrical signal allows them to change the shape of motion. So what that means is that if they presumably would put a higher frequency current through the same pathway, through the same to trigger the same neuron stimulus, they were able to change the resulting shape of the motion. So that tells us that the central nervous system is sending a signal to the muscle groups when it activates them to perform the action in a different way. Now, the interesting thing here is that when we perform an action, we will be coupling together a series of these motion primitives to build a more complex motion. So in the classical example, or the classical metaphor here, is in the same way that an alphabet forms a sentence. So we might have dozens of motion primitives all active at a time. So in their work in ETH Zurich, Grégoire Courtine has performed experiments on these decerebrated rats, and so that means that they've had spinal injury or spinal lesion, which has caused their central nervous system not to trigger the actions. And what they're able to do here is they perform the electrical stimulus, and of course they also use a drug cocktail, so there's a chemical process as well, and this triggers the mouse's walking. So, and the other thing that they were able to show is that by using a larger frequency or higher amplitude of the current, they're able to change the shape of the step of the mouse, or the rat in this case. So there's a problem with motion primitives. First of all, that if we're trying to look at an action, if we looked at a single action, there's a combinatorial complexity. So there might be dozens of motion primitives involved in some of the most common actions. So if I just measured people picking up cups of coffee or using some sort of motion resistance rig, everyone will probably do things differently. Actually, I think that's one of my later points. But the main thing is that it's very difficult to unpick those dozens of different primitives that were involved in a particular action. The second point, which is that everyone essentially is probably solving these motion control problems differently, so we don't really know which motion primitives people are going to use, and we also suspect that everyone's motion primitives are different. And the other problem is, of course, experimental ethics. If you want to do the same thing as what they were doing to the rat in the previous slide, it's going to be dangerous, and so most studies are based on observation. So this leads us to the equilibrium point hypothesis. So basically the high-level control, so the central nervous system, through either some sort of stimulus, such as our vision, or through some sort of conscious thought, specifies the action, so maybe pick up my cup of coffee, and perhaps says, gives me some qualitative properties as well. So like do it quickly, or do it slowly, or whatever, or tip it over when I pick it up. Now, the way this is often referred to is tweaking. So it doesn't actually say how to achieve the goal. It says qualitatively how to change or to adjust or adapt the motion in order to achieve the same goal. Now, how that's described mathematically, if you like, is that the central nervous system, through the electrochemical process, is specifying equilibrium points. So an equilibrium point might be the position in which my coffee cup is. So it might say, go and pick up that coffee cup over there. So equilibrium points are states in space and time in which the motor synergies, so in other words, the different muscle group activations, are balanced with each other and the environment. So that basically means that once I pick up my coffee cup, maybe there's going to be a point at which my hand needs to pass through, in which it's going to actually grab the cup. So I might be doing that in a heavy wind, or I might be reaching my arm through treacle, which I'll talk about in a second. And also another thing is that it also means that we don't need to know if the cup is full or empty, right? So the central nervous system doesn't necessarily send that information through to the rest of the nervous system. The nervous system must in turn be figuring out how to handle how to apply the appropriate forces to pick the cup up, regardless of whether it is full or empty. An experiment was done on people who have lost the sensation in their thumbs, in which they were, and also they were, their thumbs were hidden from sight, so they were essentially, their thumbs were placed in some sort of medium which they didn't know, and they had no sensory input, neither visual nor on the skin either, and they were told to move their thumb from say a extended position into an upright position. So they had to move their thumb 90 degrees, and it was shown that the central nervous system signal was exactly the same no matter which substance they were moving the thumb through. So they were either moving it through air, or maybe they were moving it through something very viscous like treacle, or some resistance was applied to the thumb to simulate that. And what they found was that people generally moved their thumbs to the upright position. So the expectation was, if the brain was involved in this process, the brain would have sent a signal as if it thought that the thumb was moving through air. And if it was sending that signal, then the force that would have been applied when it was moving through treacle wouldn't have been enough to make the thumb be upright. But it turns out that the thumbs were upright regardless of the brain signal. So what that tells us is that the processing was essentially devolved to the rest of the nervous system, and the rest of the nervous system calculated through the afferent feedback which it received from the skin or the joints, or from the muscles, what the current position of the thumb was, and also how much correction was needed to achieve the straight thumb. So, but there are many other experiments on monkeys and other animals which also validate the equilibrium point hypothesis. There is plenty of evidence, both present and emerging, that this is quite possibly, or this is the probable mechanism by which the central nervous system is controlling your motion. Okay, so now I've waffled on about that. So now I need to introduce a little bit about dynamical systems. So this is an example of a dynamical system, which was chosen for beauty rather than function. But it's an example of trying to describe motion with a curve. So here's the simplest example that I can manage. So this is a mass spring system, which basically means we have a mass and we have a spring, which has some sort of stiffness. And the mass spring system is often used as the simplest possible example of a dynamical system. So it's essentially described as a differential equation if you into that sort of thing. But what's going to happen is maybe I'll pull the mass down and release it, and then the spring will bounce for a while until it reaches a rest state. So if the spring is undamped, as in there's no rest state, it'll never stop. We'll get some sort of cycle like this. So what we're plotting here is x, which is the length of the spring, or possibly this measurement here on the ruler, and we'll be plotting it against we'll be plotting the velocity against the position. Okay, and in comparison here, if the spring is damped, then what's going to happen is it's going to bounce, but what's going to eventually happen is it's going to converge towards zero, where the spring is completely at rest. So this is an example of looking at a dynamical system as graphically. So we can look at some sort of system in motion, and we can look at it graphically, and we can also describe this mathematically as well, which is very important. So if we want to design something, if we want to model something, especially when it comes to a physical simulation, we probably need two things. So we're going to start with a mechanical model, which I'll describe in the next set of slides. But the mechanical model is essentially the components of the system, mass, length of the components, the connections, maybe our spring stiffnesses, our gravity, and perhaps the actuators as well, which need to be taken into account. And then, of course, we have a control strategy, which is basically how we input into the system. So in this system, there's going to be a collection of actuators, and those actuators can be controlled using some sort of software or something derived from the senses, which is going to send the appropriate signal to each of these actuators and cause our robot to start walking. So this is a very general principle. Generally, these two things have to be developed in concert, so you can't really start developing a control strategy until you have a mechanical model in place, and vice versa. But as a general design principle, we're going to start by saying that we probably want to make the mechanical model, first of all, simple, but secondly, we also want it to do most of the work. So we want the mechanical model to hopefully be stable by itself. And that is actually how we walk. So we use very little energy when we walk. And I think the principle here is to try and emulate nature as much as possible. So this one might be a little bit tricky to digest if you're not of a mathematical background, but a dynamical system has a number of properties. So if we go back to if we consider the mass spring system, when it was continually going on a loop in a undamped system, that loop that it converged towards is considered to be the attractor. So the attractor is the limit cycle, the point. So it's essentially a pattern that repeats over and over again. So and that is actually the desirable property for these systems. So depending on the starting conditions of that mass, it will always converge towards the same limit cycle. So but another type of attractor is a point attractor. So it might be the spiral one, where the system was damped, in which case it spiraled down to the central point and then stopped. So those are two different types of attractors. Another attractor which we don't really consider is chaos, because that's a little bit outside of our comfort zone. But let's consider point and periodic attractors for now. And actually, periodic attractors are considerably more interesting from a locomotion perspective. So the limit cycle is, as I've said, is the periodic attractor to which it converges after running for a while. And another thing is the basin of attraction, which is the region around the limit cycle, where if we started in a position in that space, we would converge towards the limit cycle and ultimately end up on the limit cycle. If we were outside of that basin of attraction, and we picked a state outside of the basin of attraction, it would be unstable and our robot would probably fall over. The sink is a good example of an attractor. So this is the water is flowing down, you can see it spirals down, and ultimately it's going down to this point attractor. And this, in a similar example, this is now spiraling down and ending up on this periodic attractor, which is going in this pattern, repeated pattern. Right, so the adaptation that we're trying to describe here is to basically say that we can describe the motion in terms of their dynamical properties. So the dynamical properties going back here are the type of attractor, which is either point or periodic, the position and shape of the attractor, right, and the region of stability. So this region of stability, the basin of attraction, is also part of the dynamical properties. So the complex muscle models, if we just observed our motion, rather than trying to model the complexity of the muscles and all of the other complexity that we have in the human body, and we just observed those motion patterns, we could consider these to be a dynamical system. And we could also derive expressions or equations of motion for this dynamical system. So if we have the equations of motion for this dynamical system, we can then start talking about some maths which will help us change the shape of this dynamical system without altering the properties. And again, those properties are the basin of attraction, the fact that it is a limit cycle attractor, and things like that. So if we can do that, if we can tweak this dynamical system without changing its properties, we've achieved motion adaptation, which is basically the fundamental premise here. So here Fangde Liu is dropping a ping pong ball onto a pedal there. Let's play that again. So in this particular example of the dynamical system, nothing's happening. The ball's being dropped. It hits the paddle. Some energy is lost. Okay, this one is obviously the synthetic system is obviously bouncing a little bit, so it's a bit the paddle is a little bit more a little bit less. It's not taking as much energy out of the system on each bounce. But I think you get the idea. And eventually it's going to converge towards the single point. So in this particular example, he's actually providing an upward velocity which is causing the ball to bounce off the paddle. And it doesn't matter where, so these X's here indicate a number of different start locations for the paddle ball to be dropped. And it doesn't matter where the paddle ball was dropped, it always converges towards this red limit cycle. Okay. So what we want to do now is we want to define some sort of transformation which allows us to change the shape of that red limit cycle. So here's some maths in a kind of a hand-wavy way. So what we're going to try and use is something called symmetry preserving transformations. So remember we have a formula which describes our dynamical system, and it's going to be probably a second order differential equation. But what we need to do basically is to transform the structure of our system so that we change the shape of the dynamical system without changing its properties. So, symmetry preserving transformations, to try and explain this, and this is the normal example which is used, if I have a circle and I apply rotation to the circle, so a rotation around the center of the circle, I will get a rotated circle. So it'll still look like a circle. So if I said that the invariant that we want to preserve is the shape's circleness, then rotation is a symmetry preserving transformation of a circle. Okay, so this is very important. So the symmetry condition in this case is that it remains a circle, or it remains the input shape, or equivalent to the input shape. Now if I apply the same transformation to a star, there's only going to be a small number, say 5, rotations that I can apply to that star so that my star looks exactly the same. So if my symmetry condition was that my star looks the same as my initial star, or the invariant that I want to preserve is that, then rotation is not the symmetry preserving transformation of the star. Okay, so given that, we can say that our symmetry condition is the shape of the dynamical system. And actually, when we talk about the shape of the dynamical system, we are really talking about the laws of physics actually being the invariant, but let's not dwell on that. So if we define that our symmetry condition is the shape or properties of our dynamical system, then we can create a set of transforms that allow us to tweak the dynamical system. And this basically allows us to define some low-dimensional controllers, so very simple controllers with some very, like, 1 or 2 parameters that'll allow us to do some very complex modifications to the dynamical system. So here's an example where our Fangde is banging the paddle ball a lot higher, and this red curve is what results when you apply a transform to scale it up. So what's happening is essentially he's applying more velocity to the paddle when making contact with the ball, and that's in essence the symmetry preserving transformation at work. So we find that this actually happens in nature. So this was another colleague, Shihui, who we strapped into a motion capture suit, and we put him on a treadmill in a variety of different scenarios. So the first scenario was to manipulate the speed of the treadmill. So he was walking on level ground, and of course this data is very noisy, so we had to average it out. But what it results in is you'll see an obvious changing in the shape of the curve as speed increases. So as speed increases, you'll see that the curve is essentially scaling bigger and bigger. So he's walking more energetically when the speed increases, and obviously the velocity of the curve is increasing, and his step size is also increasing. So that's quite interesting. But also we notice when we change the elevation of the treadmill, so here it's 0 degrees, 1.9 degrees, and 7.1 degrees, but the treadmill's speed is constant, we see that he also has to, so the curve essentially is shifting to the right, so there's an offset, if you like, in the direction of Q, to account for the change in slope, and also he's walking more energetically. So these are examples of adaptation of a real person on a treadmill. So using exactly the same walking method, so it's the same kind of mechanical system, if you like, but has now changed their walking to account for the changes in slope and speed. But I think the key thing here is that the curve is the same shape, right? So you can argue that these shapes are equivalent, but they have been tweaked, as in they've been offset or scaled because of the adaptation that's taken place. And that's essentially what we're trying to model. Okay, so this all boils down to one big message here, which is that the symmetry preserving transformations I'm saying are equivalent to the equilibrium point hypothesis, but essentially they are realizing the equilibrium point hypothesis, or allowing us to model the equilibrium point hypothesis on synthetic models. Okay, so now I'll talk about model for locomotion. So these are two different, obviously there's Asimov walking, and then there's someone doing motion capture on a treadmill, and you can see that their gait is very different. So locomotion is a difficult thing to model, and on Asimov it's he's got a large battery pack there, so he's not very energy efficient, and the human, in contrast, is effortlessly walking, and the motion of Asimov as well looks kind of stiff because he's using a lot of what we call a high gain controller. So he's using a lot of excess energy to ensure that he maintains balance. So what we really need to do is we need to and the other thing to mention is that Asimov is probably using between 25 and 50 times the amount of energy of our regular human runner. So it is actually very difficult to design these models, and it's difficult to design controllers which will be able to adapt to these new environments. So a design principle is to perhaps start with a mechanical model that actually consumes zero energy. So, and here's one. So this is a classic toy robot which is walking down a slope. So it's being propelled forward by essentially potential energy because of the gravity. The robot itself has no actuators in it. It's just being propelled forward by gravity and the potential energy of it standing on the slope. So that's all good and well, but oh, wait, I've lost my mouse. There we go. Here's a modern, or a slightly more modern or up-to-date equivalent. So this is a model developed by Collins, Renaud, and Drake and Visser at Cornell University, and their model was able to demonstrate a much more natural gait was possible by designing a robot based on these passive dynamic design principles. So passive means that it doesn't have any energetic input. There's no actuators on this thing. It's completely free from any energetic input. And of course, it's a dynamic model because it's in motion. And it's driven by potential energy alone. So obviously, it doesn't need to be steered by someone. But here it's walking down a slope with very little intervention except for someone stopping it from falling over. And it's based on the idea of straight leg vaulting dynamics. And it's very easy to model this. While it is easy to model, it's actually quite difficult to make it stable. So another thing to talk about passive dynamic models is that it's a good way of understanding the gait of other animals as well as humans. So in this particular case, so this comes from a paper by Usherwood and co-workers, and this demonstrates that, well, in the paper anyway, they demonstrate that the compass gait dynamics are a very good way of understanding both waddling ducks and humans in their gait. So we took this model and we applied the motion adaptation principles. So this is the model, sort of a synthetic version running on a downhill slope. So if we tilt our robot downhill, it'll walk unaided, and we'll use this as our reference gait. So there's absolutely no actuation on this one. But if we change the slope so that it's on level ground, of course, if there's no actuation, there's no potential energy, and ultimately our little robot will fall because it will run out of energy. So what's happened here is our robot has failed to adapt to its environment, and he's going to fall over there. Right. So what we want to do then is we want to apply one of our transformations, our symmetry preserving transformations. So the symmetry preserving transformation is going to shift the robot. So apply an offset just like what we had on the human walker, and rotate the hip angle. So what we've got now is our robot is walking on level ground, and I don't know if you can actually see it from the example, but it's slightly tilted backwards, which is quite possibly what we're doing anyway when we're walking on a slope or on a level ground. And you can see that it's converged towards a stable limit cycle there. And another thing to say is this is at a very, very small additional energy cost, and in fact it could be argued that this is an optimal energetic cost for adapting to level ground. And what we can do also is, this is an example of increasing the step size. So we're going to scale it. So note it takes a little time to adapt to the adjust to this to get into its stable limit cycle. But now what we've done is we've qualitatively changed the gait by shifting the step size. So what's happened is that the limit cycle has essentially grown in the x direction, and it makes the gait more energetic. Right, so those are some examples of applying the principles of symmetry preserving transformations to achieve motion adaptation of a dynamical model, which in this case is the passive dynamic walker. So to conclude, locomotion modeling is multidisciplinary, so there's quite a number of different discipline areas in that list, but we can certainly argue, based on some of the earlier stuff that I talked about, it's quite useful. It should be helpful in building bipedal robots, certainly. It is helpful in stroke rehabilitation. We'd like to apply it to character animation. And of course it's useful in understanding how locomotion evolved. And And of course, then we still have no consensus exactly on motor control mechanisms in nature. So I think there's certainly no consensus that the equilibrium point hypothesis and by extension the uncontrolled manifold hypothesis is in fact the mechanism that is being used. But this is obviously an area that people are working on. Modeling and simulating full musculature is extremely difficult. There are researchers who do this, but constructing these models and expecting them to be stable is it's quite optimistic. Making them adaptive is also very difficult without prior knowledge. So you probably need to train your models based on all the expected types of environmental changes before you can actually, it'll be part of the control strategy, it'll be built into the model, which is an expensive process. So one would argue that if I just had a mathematical transform that I could apply in most cases, it would be a lot more cost effective and allow us to adapt to a lot of different types of environments. But another thing to stress is that there is no existing model that is stable, as energy efficient and adaptable as a real human. And what we'd like to do is use these kinds of simple mechanical models and biological principles to develop controllers for them. And ultimately, we'd like to build a robot with somebody. But that's all future work. And that's it. So there's my details. Get in touch if you're interested. And that's that.